this cinema. Without your presence, this event would have been incomplete. We are truly thrilled to present our hard work here on this beautiful day, as we have waited for this moment dearly. You see, all this knowledge we have accumulated in the last few weeks, it came at a cost. And I'm glad it was just our time and not our sanity. Please remain seated and enjoy our work of art.
Hello everyone, I'm going to introduce you all to the topic satellites. Whenever we think of the word satellite, we have the tendency to think of it as a machine that is launched into space and moves around Earth or another body in space. However, satellite can either be a moon, planet, or machine that orbits a planet or star. For example, Earth is a satellite because it orbits the sun. Likewise, the moon is a satellite because it orbits Earth. Earth and Moon are classified as natural satellites. What natural satellites are, we'll tell that later. Thousands of artificial satellites or man-made satellites orbit Earth. In 1997, it was found out that there are 2,271 satellites in orbit. We've updated that information, and satellites are man-made machines, so they have gone out of date, and now we're having 1,305 satellites currently in orbit in outer space. The thing is that over here you can see the definition of satellite. By this definition, it can be literally anything. It is only defined to be a satellite orbiting the Earth, the Moon, the Sun. It can go to being black holes orbiting each other. That's one black hole can be the satellite of the other black hole. Galaxy can be a satellite of a much larger galaxy being orbited, and so on. Now I'm going to move on and explain you what are natural and artificial satellites. Natural satellites are those which are already placed in object by the creator himself. Those are not man-made. They're already in place on space. Artificial satellites are the man-made machines we have launched into space over the year. After the first satellite was launched. We have a look for more information about natural and artificial satellites.
Now for a crash course in history, here's Abdullah.
As you might be aware that there are thousands of satellites in orbit around our Earth. But I believe you might be intrigued to know about, you might be intrigued to know But I believe you might be intrigued to know about the first man-made satellite that was launched in the history of mankind. Then allow me to take you to a journey back in time, the day history was made. While the Americans were still finalizing the plans, Sputnik 1 was launched by the Soviet Union. It marked the beginning of the USSR space race. The R-7 rocket in Sputnik into space. Its case open and the screen snapped. The spare before antenna. Spare before antenna. Sputnik. The radio signal started transmitting. Alas, that's not all of it. The true hysteria began when Sputnik 2 was launched, and this time with a dog named Laika on board. Russians, they did not only manage to send the first satellite to space, they even managed to send the first creature to space. They did not only manage to send the first satellite, they also managed to send the first creature to space. But Russia was not yet done. They managed to send the first man to space, Yuri Gagarin, in 1961, and the first woman, Valentina Tereshkova, in 1963. But do you think America liked being second to Russia?
Yes. Why not?
Let me spell it out to you. No way on earth. And all this led to the authorization and formation of the U.S. space program, NASA. Surprisingly, America, fueled by the collection of Nazi scientists, managed to send a second person to space, Alan Shepard, on May the 5th, 1961, just a mere month after Yuri's journey to space. The Russians have won battles after battles, and it seemed that the Cold War had been favoring them from the very beginning. But unfortunately, it was the United States of America who have won the war. And in 1969, July the 20th,
Why are we cheering?
Neil Armstrong became the first man to set his foot onto the surface of the moon. But in the end, Sputnik was the spark humanity needed to explore the cosmos, to dive into the unknown darkness and depth of the universe, to put man on the moon.
Now our scientific researchers, Nabil, will come forward.
When we started the seminar, one word we were associating a lot with the term satellite. That word is orbit. Now what is an orbit? An orbit is a path taken by an object revolving about another. It is usually elliptical, means it's circular. Now there are two main types of satellites, geostationary and polar. A geostationary satellite revolve the Earth with a time period same as the Earth, which is 24 hours, and it's usually at the equator. Then we have polar satellites. Polar satellites revolve around the North and the South Pole, and they are 90 degrees to the equator. Now here's a basic example of how the geostationary satellite works. For example, when we are broadcasting a signal, for example a live match or a TV show, we use geostationary satellites because when we transmit a signal, we need to make constant link between the satellite dish and the satellite itself. So for that reason we need geostationary satellite because so then we don't need to move the dish around continuously. And then polar satellites are mainly used for monitoring purposes, for monitoring environment, weather, etc. Here's a comparison between geostationary and polar orbit. First is related to the time period. The geostationary orbit, the geostationary satellites takes 24 hours to complete the orbit, and the polar satellites take only a short amount of time. The second is the direction of their rotation, which is for geostationary west to east, and for polar from north to south, or from south to north. And their positioning around the Earth for geostationary is fixed, and for polar, it's constantly moving. And now one thing we can notice from the diagram over here is that the radius of the geostationary orbit is much more bigger than the radius of the Earth. So the geostationary satellite must move with a greater speed, so it looks stationary to the Earth. The polar satellites are moving much more faster because they are closer to the Earth.
Thank you for the speech, and I hope you understand. Now, what we have here are the basic principles of satellite. This includes the motion, where we'll explain how a satellite is launched and why does it remain in a constant orbit around the Earth or any other planet. And then we have communication, which will cover most of the syllabus content of satellites. Let us begin with a simple theory. If you project something out into space at the correct trajectory and the correct velocity, it will remain there orbiting the planet for years. Now the tricky part about this is the balance between gravity and the velocity. If they are unbalanced, for example, if the speed is higher than normal, the satellite will move away from the planet, whereas if it's lower, it will fall back into the Earth. The reason this works is because of the gravitational force of the planet and the inertia of the object. Now as we can see here, this net force, it has to match the gravitational force. Now to match it, if it matches it and the velocity is accurate, it will always remain in a constant orbit. This force, it doesn't remain constant, it changes with that altitude. Now if the altitude is higher, the force experienced by the satellite will be much lower. This is why it will move at a slower velocity, unless it's a geostationary satellite, because those satellites need to be in proper orbit. Here, the difference in altitude, we are only considering medium Earth orbit, which are between geostationary and polar. So now, for the same way, if the satellite is lower to the Earth's surface, for example, the International Space Station, it will have to move at a much higher speed. For example, the International Space Station moves at a speed of 7.8 kilometers per second. That is roughly 28,000 kilometers per hour. Here we have a simple video of a simulation showing how the satellite is launched. The rocket that carries the satellite up into space is known as a launch vehicle. It will escape the Earth's atmosphere and reach a certain height, the altitude at which the satellite will escape. You can see the altitude is increasing over there, and after a certain period of time, it will start to tilt in a curved trajectory that brings it nearly parallel to the Earth's surface. Now this is where the rocket will burn its last remaining fuel to reach the orbital velocity, the velocity at which the satellite will maintain a constant orbit. So now we can see that as I would like to point out, this is where the fuel we are seeing. Now when When it has reached the correct orbital velocity, the satellite is released. And since it's released perfectly, it will remain there for years. Unless it collides with something that comes later. Now, we're having the principles of satellite communication, and Mama's coming out to explain the key definitions.
Before explaining the principle of satellite communication, we need to look at a few key definitions. What exactly is modulation? In electronics and telecommunication, modulation is a process of varying one or more properties of periodic waveform. Carrier wave, a high-frequency electromagnetic wave, modulates the amplitude or convey or frequency to convey a signal. Attenuation refers to any reduction in strength of a signal and it is being transmitted. And there are four key questions when it comes to principles of satellite communication. How does a satellite receive or transmit signals? And first of all, we need to understand what exactly are the uplink and downlink signals. Uplink signals are those signals which are being transmitted from Earth stations to satellites. They are of high frequency and high power. Downlink signals are those signals which are transmitted from the satellite back to Earth, which are in much lower frequency, and we will get to know why they're in lower frequency later on. How do the signals travel? As I mentioned about carrier waves earlier, the signals are delivered by carrier waves, modulated by frequency, amplitude, or other methods. Each signal has its own frequency and bandwidth. If you look at the diagram over here, you can see that the uplink is going up over here to the satellite, and the downlink is coming back to the Earth station. And the satellite is a geostationary satellite up there. And Nabil explained about geostationary satellites. Where the uplink and downlink frequencies differ. The uplink frequency is of higher frequency and of high power. Because without having a high frequency, the signals cannot penetrate the Earth's atmosphere in order to reach the satellite. As a result, we need to also provide high energy for that. Because as the signal reaches the satellite, because of attenuation, it loses a huge amount of energy. And because the satellite is going to send out to Earth, is going to be of high power, and as it receives low powered signal, because of that, swamping takes place. Because of that, we have to be very careful of not messing up the power and frequency. As a result, how is a satellite able to maintain a continuous communication between places? As Nabil told about geostationary satellites, which is almost stationary compared relative to the motion of the Earth, it is stationary. Because of that, we don't have to move the antennas and all that. We can just place them in stationary position and have the signals there.
Thank you, Mona. And now, Murzu and Asam are going to come forward and tell us what makes satellites so important.
Now, as you know, satellites are launched into space with specific purposes in mind. Different satellites have different purposes, and obviously, they vary in size and shape. Like satellites that monitor cloud pattern are going to be different from the satellites which receive and send TV signals.
Now, what makes this technology so essential? The answer may vary, but you will hear one word repeated a lot: communication.
Phone calls, broadbands, and broadcasting, all of these are different from communication which require satellites.
GPS systems are only able to work because satellites can map a large portion of the Earth at a fast rate.
Okay, now TV signals and phone calls are transmitted much faster over longer distance. This is one of the reasons why satellites have become more important at this point of our life. Okay, now moving on to the next slide. Okay, now as you see over here, the use of satellites are given. The first one is broadband digital communication, which is used by consumers and businesses is basically high-speed internet, which is provided by telephones and for many other use. Now the second one, which is direct broadcast service, which involves the broadcasting to general public. Satellite dishes are usually used for this purpose.
Warning, reception may be affected by solid objects in front of the satellite dish, clouds, or your government jamming circuit.
Now the third one, which is mobile satellite services, which are constantly providing communication to service, mobile and GPS systems.
And on a different note, we also have environmental monitoring satellites. These satellites have highly sensitive sensors and sounders, which can detect tiny fluctuations in the atmosphere, and they help us to forecast the weather. Now, this is just one of the functions of satellites. As you can see, there are other functions over here.
For example, for the first one, like Earth observation, they're both used by civilians and military, and they're usually called spy satellites.
I'll show you a picture, but it's classified. Now, space exploration satellites can orbit other planets and moons and provide us information about them. An example of this is this satellite here. It's called the New Horizons, and it took the first picture of Pluto.
Okay, now the last one is the scientific research satellite. These satellites gather data for scientific analysis, and they usually give us usually give us the observation of the atmosphere and the stars and the other objects in the space.
There is one satellite that can perform all three of these functions and more. It's called the International Space Station, or ISS for short. Now, the ISS was made by several countries as a cooperative project. On the ISS, astronauts live and perform scientific experiments. I would tell you the experiments, but apparently it would be too long if I did.
After all this talk of satellites, one question arises. Do satellites ever crash into each other? What do you think?
I think it is impossible at this time of our life. There are usually systems and people tracking the satellite, and maneuvering its course if in case they crash.
That is quite accurate. However, collisions still do occur. In fact, the first ever man-made satellite collision occurred only 7 years ago.
The first one was an US-built satellite, which is called Iridium 33, which collided with a Russian decommissioned military satellite.
NASA estimated that the amount of debris formed from this collision was approximately 100,000 pieces, which are more than 10 centimeter in length. However, there were many more that could not be tracked.
Before 2009, there were many minor collisions between debris and some satellites. These were very small, not that small.
Nowadays, there are more precautions to avoid such incidents. In fact, there are websites that can track these satellites in real time. An example of such a website is Celesttrack and NASA JTrack. These are both useful, which show you if you had internet access.
Nowadays there are laws in some countries which require all the geostationary satellites to move into a new orbit, which is known as the graveyard orbit, and at the end of the operational life.
As we already know, collisions can form a lot of debris. Now, what happens to this debris? How about I let the video explain for itself?
Debris, which is any man-made object in orbit around our planet which doesn't serve any useful purpose, is becoming an increasing problem. We're currently tracking around 600,000 pieces of debris larger than 1 centimeter. Roughly 30,000 of these are only 1 decimeter wide, but there's still many hundreds of millions of pieces which are simply too small to keep track of. What's so dangerous about these seemingly insignificant tiny fragments is the speed at which they travel. They orbit the Earth at speeds up to 28,000 kilometers per hour. Even something as tiny as flecks of paint can be disastrous when traveling at these velocities. In fact, a number of space shuttle windows have been replaced simply because of damage caused by flecks of paint. Usually, when a tracked piece of debris is about to collide with a functional spacecraft, a so-called debris avoidance maneuver is performed. This actually happens all the time, and even aboard ISS, in which the entire space station is moved a few kilometers to avoid a potential collision. But the thing is, we may already have crossed the point of no return. Even if we stop sending anything into space right this moment, it will continue to get worse. You see, the amount of debris which is already in orbit will continue to collide with each other and thus create even more debris. So far, the problem is manageable, but a solution needs to be found quickly. And while NASA and many others are working on solutions, it's not an easy problem to solve. I mean, the sheer scale and cost of resolving this issue is like nothing we've ever seen before. And if we do nothing, we will quite literally enclose the Earth in a blanket of garbage.
So now we'll be doing some past paper questions. Can't see it. Zoom in. You see me wearing glasses. Thank you. A ground station on Earth transmits a signal of frequency 14 gigahertz and a power of 18 kilowatt towards a communication satellite orbiting the Earth, as illustrated in Figure 12.1. So you have the satellite here and the ground station here and the signal right here. The loss in signal power between the ground station and the satellite is 190 decibels. Calculate the power of the signal received by the satellite.
Elevation is the 10 log to P1 divided by P2. So attenuation is 190 decibels. So 10 log is P1, that's the pressure, which is 18 10 to the power 30 given there, kilowatts power. And P2 you can find it with the equation that's 7.8 and 10 to the minus 15. Now the second question is
The signal received by the satellite is amplified and transmitted back to Earth. Suggest the frequency for the signal that is sent back to Earth.
so now you can say it's 11 to 12 any gigahertz because you know.
So the reason is, it is so that the input signal is not swamped.
That is exactly why I explained that the uplink and the downlink signal cannot be of the same frequency because of this exact reason. This exact question tells us about the exact reason.
State two reasons why frequencies in the gigahertz range are used in satellite communication.
Gigahertz frequency signals are not reflected by the ionosphere. Because if they are reflected by the ionosphere, the signals are going to be blocked and they will not be able to reach the satellite. The second one, a large amount of data can be transferred to the satellite.
In one particular satellite communication system, the frequency of the signal transmitted from Earth to the satellite, the uplink, is 6 gigahertz. The frequency of the signal transmitted back to the Earth from the satellite, the downlink, is 4 gigahertz. Explain why the two signals are transmitted at different frequencies. It is to prevent swamping at the uplink of the uplink signal by the downlink signal, as explained by Mandar earlier.
Last one. The signal transmitted from the Earth has a power of 3.1 kilowatts. This signal received by a satellite has been attenuated by 185 decibels. Calculate the power of the signal received by the satellite. So again, the attenuation is equal to 10 log E, the power of the first one divided by the second one divided by 1. So attenuation is 185 equal to log 10. 3.1 and then 3 we just put it right and then so power is 9.1 to the power minus 16.
We're officially at the end of our presentation.
Is there something you haven't understood? We can explain it.
Oh yeah, sure.
If you have any doubts, please go ahead. Swamping.
Well, for example, we have learned about waves. Mr. Shakir taught about waves and everything. And it can't have the same frequency. It cannot have the same frequency. Without the same frequency, they'll cancel each other out. There is a huge factor in this case. That's why the thing is that if we are sending a signal with high frequency and with low power because of attenuation, it's of low power, and the signal is to be transmitted by the satellite to Earth back with high power. So we don't want to interfere with all of these, you see. That's why we call it. You guys have any more doubts?
If there's no more doubt, shall I continue? Okay, now we are officially at the end of our presentation, and we have prepared a small video showing us the Earth. Let the video speak for itself.
This video was taken from ISS, International Space Station.
It's a lot of CGI.
It's real. And you can see the lightning sparks over there.
First of all, I found this footage from NASA. If NASA is lying to us, I don't know who to trust.
They faked the moon landing. They're not faking it. This is real.
Hey, how dare you insult Neil Armstrong?
The video. We will have seen a much better video of this.
You might have noticed the silence because in space there's no sound.
In other words, no one can hear you scream in space. You're probably gonna. Unless you're in a spacesuit.
That's the Aurora Borealis.
Fun fact, if you're ever in a spacesuit, and you find out your radio is not working, you can actually scream and bump your helmet against your partners, and it will create a bridge for the sound to travel. So technically, you can hear someone scream in space. You'll just have to scream really loud.
Your partner may not be able to help you if he's dead.
A few years ago, a man drowned in space, almost drowned in space. They found out that his cooling liquid, it leaked into the space, his spacesuit, and started filling up his helmet. He remained calm. This is a quality astronauts need to follow. Remaining calm under pressure. That man almost became the first person to drown in space, yet he was completely calm. That's why he's